Hello, Matt here from ChemistryStudent.com. In this video, we're going to look at Hess's Law. We're going to talk about what Hess's Law actually is, how we can use Hess's Law to find enthalpy changes with Hess cycles, and show this using the formation of propane as an example. Enthalpy and enthalpy changes have been covered in separate videos. Check the links in the description below. Before we talk in detail about Hess's Law and Hess cycles, there are a few essential ideas you need to be comfortable with. Enthalpy is the heat content or thermal energy store of a substance or system. All molecules and substances have thermal energy stored up inside them, as when some of their stored energy is released, it can only flow out in the form of heat. Enthalpy change is defined as heat energy change, kilojoules per mole, measured at constant pressure. It is impossible to know the exact enthalpy of a substance. It is possible, however, to measure how the enthalpy of a substance changes when it reacts. This means in chemistry we work with enthalpy changes, shown as delta H, rather than total enthalpy values. Standard enthalpy changes are used to ensure enthalpy changes can be compared for different reactions, as the temperature and pressure at which a reaction occurs affects the enthalpy change measured. For an enthalpy change to be standard, measurements must be made at 298 Kelvin and a pressure of 100 kilopascals, with reactants in their standard states. Standard enthalpy of combustion refers to enthalpy change that occurs when 1 mole of a substance is completely burnt in oxygen under standard conditions. Standard enthalpy of formation refers to the enthalpy change that occurs when 1 mole of a substance is formed from its constituent elements in their standard states under standard conditions. Recap done? Let's go! We know that the enthalpy change of a reaction is based on the difference in enthalpy of the reactants and products. It's a bit like the height you climb when climbing up a mountain. It's based on the difference between the altitude at the bottom of the mountain and the altitude at the top of the mountain. Hess's law states that the enthalpy change that occurs when a particular set of reactants are converted into products is always the same, regardless of the route taken. It doesn't matter how you turn the reactants into products, the overall enthalpy change will always be the same. Just like climbing up a mountain. There may be more than one way to get up a mountain, but it doesn't matter which way you climb or the route you take, even if you stop halfway up for a rest. By the end, you will always have climbed the same height, as the difference in altitude between the start and end points is still the same. Sometimes in chemistry, there is more than one possible way to turn one set of reactants into particular products. An imaginary reaction between A plus B plus C to form D and E, for example, may be possible in one direct go, or it might be that A and B could react to form X and Y, and they may then react with C to form D and E. Using the mountain example here, but with energy rather than altitude, we can see that to go from A plus B plus C directly to D plus E has the same enthalpy change as going from A plus B to X plus Y, and then from X plus Y and C to D and E. There are two possible routes, route 1 and route 2. The enthalpy change for both routes is the same. Route 1 enthalpy change equals route 2 enthalpy change. This is what Hess's law tells us. This may not seem very relevant or helpful, but often in chemistry it can be hard to experimentally measure the enthalpy change for certain types of reaction. However, by drawing out a simple triangle showing the possible routes for converting reactants into a particular set of products, a simple cycle is formed, and it is possible to find the enthalpy change for part of a route that can't be found experimentally, if all the other enthalpy changes are known. This type of diagram or cycle is called a Hess cycle. Let's look at a specific example, the standard enthalpy of formation of propane, C3H8. The standard enthalpy of formation is the enthalpy change that occurs when 1 mole of a substance is formed from its constituent elements under standard conditions. Constituent elements refer to the elements that make up a compound. The constituent elements of propane are carbon and hydrogen. Under standard conditions, carbon is a solid and hydrogen is a gas, H2 molecules. To form 1 mole of propane, 3 moles of solid carbon and 4 moles of hydrogen molecules are needed. Under standard conditions, this reaction is never going to realistically happen, meaning measuring the enthalpy change experimentally directly is impossible. However, 3 moles of carbon and 4 moles of hydrogen can be combusted easily under standard conditions to form 3 moles of carbon dioxide and 4 moles of water. Propane can also be combusted under standard conditions to form, surprise surprise, 3 moles of carbon dioxide and 4 moles of water. This means we can draw a simple cycle, a Hess cycle, using these enthalpies of combustion that we can find experimentally and the unknown enthalpy of formation of propane. We can go straight from the 3 moles of carbon and 4 moles of hydrogen gas to 3 moles of carbon dioxide and 4 moles of water, or we can, hypothetically, react the same amount of carbon and hydrogen together to form 1 mole of propane that we can then convert to the same 3 moles of carbon dioxide and 4 moles of water. We are essentially using 2 different routes to go from the carbon and hydrogen to the carbon dioxide and water. Remember Hess's law, the enthalpy change that occurs overall will be the same for route 1, directly combusting the carbon and hydrogen, as for route 2, forming propane and then combusting the propane. Just like climbing our mountain, although in this case it's a bit more like coming down the mountain as the enthalpies of combustion are always exothermic and there is a negative enthalpy change. The top of the mountain is like the carbon and hydrogen, and the bottom carbon dioxide and water. Route 1 is going straight down in one go, combustion of carbon and hydrogen. Route 2 is going down in 2 stages and rested in the middle. Formation of propane from carbon and hydrogen, and then combustion of propane to get to the carbon dioxide and water. We can measure the standard enthalpies of combustion here really easily. Standard enthalpy of combustion for carbon is minus 394 kilojoules per mole. For hydrogen, it's minus 286 kilojoules per mole, and for propane, it's minus 2,220 kilojoules per mole. In route 1 of the cycle, 3 moles of carbon and 4 moles of hydrogen are being combusted, meaning a total enthalpy change for route 1 of minus 2,326 kilojoules per mole. Route 2 is made up of 2 enthalpy changes, the theoretical standard enthalpy of formation of propane and the combustion of propane, minus 2,220 kilojoules per mole. Remember Hess's law tells us that route 1 equals route 2, meaning minus 2,326 equals the standard enthalpy of formation of propane plus minus 2,220. With some rearranging here, the standard enthalpy of formation must equal minus 106 kilojoules per mole. So, mini recap. We found 2 possible routes for converting a set of reactants into products and drew this as a simple cycle. The first route was the direct combustion of 3 moles of carbon and 4 moles of hydrogen. The second route was the reaction of 3 moles of carbon and 4 moles of hydrogen to form 1 mole of propane that was then combusted. Hess's law tells us that both of these routes will have the same overall enthalpy change, meaning route 1, combustion of carbon and hydrogen, equals route 2, formation of propane and combustion of propane. Substituting the values for the combustions involved meant we could find the unknown value, enthalpy of formation for propane. It is tempting when you get a bit more experienced with Hess's law to just jump straight into the maths and find the unknown enthalpies straight away. I strongly advise you always take the few seconds to draw out a simple cycle though. It really does help with making sure your negative and positive signs are correct for different enthalpy change values. There are other ways you can approach simple Hess cycles like this, and as long as you get the right value, no one is better than the other. In my experience, this method tends to lead to fewer mistakes and is hopefully straightforward to follow. Things to be really careful of include making sure you pay attention to how many moles of a substance is being combusted or formed. In our example, we had to multiply standard enthalpy of combustion for carbon by 3, as 3 moles of carbon were being combusted, and the value for standard enthalpy of combustion is per 1 mole. When putting values into a calculator, I would always advise using brackets. Then you don't have to worry about changing any positive or negative signs around. Just put the values in the calculation exactly as they are given and let the calculator do the rest. So, to summarize, the enthalpy change of a reaction is determined by the energy of reactants compared to products. Enthalpy change is the difference between the two. Sometimes there is more than one way or route to go from particular reactants to products. Hess's law tells us that the overall enthalpy change for the conversion of a set of reactants to products is the same, regardless of the route taken, assuming initial and final conditions are the same. It is possible to find the enthalpy change for a part of a route if all other enthalpy changes are known. This can be done using Hess cycles, where both possible routes are drawn out with all enthalpy changes shown. Hess cycles are useful to help find out the enthalpy change of a reaction that will be hard to measure experimentally. For example, enthalpies of formation. I hope you found this video useful. Please check out other relevant videos in the links given in the description below and visit chemistrystudent.com for free notes and revision materials.